Hi there, and welcome to the Fibre Channel Industry Association. Today we're going to be talking about the fundamentals and basics of Ficon. Why Ficon? Well, because whenever we talk about Fibre Channel, we almost always refer to the x86-based data centers, with Fibre Channel attached arrays, edge-core edge topologies, and the like. And we often ignore the giant elephant in the room. And that's the bedrock for mission-critical applications, the mainframe. And along with it are the interconnects, also known as Ficon. Now, I have to confess, one of the reasons why I wanted to moderate this webinar was because I simply didn't know anything about mainframes or Ficon. And quite frankly, I was embarrassed to ask the stupid questions. Now, maybe you know an awful lot about Ficon already, but if you're like me, then I think you're going to really like this presentation. So my name is Jay Metz. I'm on the FCIA Board of Directors, and I work for Cisco. But I'm going to step back and shut up so that our true gurus and experts can step in. We're really fortunate to have the two masters of the craft. And I can honestly say that I'm very excited to be hosting Patty Driever of IBM and Howard Johnson of Broadcom, both of whom have long histories of Fibre Channel standards development in the T11 group. One quick word of housekeeping. Before you ask, and everyone asks, PDF of this slides are going to be available at fibrechannel.org after the conclusion of this webinar. Also, if you're listening to the audio from within your browser, sometimes it may be difficult to hear, and we found that emptying the cache or refreshing the page often helps. In addition, any questions that we're unable to get to today, I expect that there probably will be quite a few, will be collated into a blog that will also be posted to fibrechannel.org. So please feel free to ask away. However, we have a lot to go over today, and since you didn't come here to listen to me yammer on, I'm going to ask Patty to take us down into the wonderful world of mainframes and Ficon. Hi, Patty.
Hi, Jay. Thank you so much, and thanks for giving us this, thanks to you and FCIA for giving us this chance to introduce Ficon and mainframes to maybe an audience that isn't quite so familiar with it. So because Ficon is unique to mainframe servers and it's really purpose-built for that environment, stepping back and first understanding that world of the mainframe is key to understanding Ficon. So that's the first thing we'll do. The second thing is, this is where Howard's cleverness comes in, is he created this moniker, this mnemonic, is faster. And at the end, hopefully you can take away one thing from this to remember about Ficon and mainframes is this acronym of is faster. And we'll talk about what all those letters stand for as we go along. And then lastly, we'll get into an overview of Ficon. Once you understand that context of Ficon on the mainframe, we'll delve a bit into the how, but honestly, I'll be upfront, not very deep, because it's very hard in 45 minutes to an hour to really teach Ficon, right? It's really going to be an introduction, and we'll reserve anything for a future 201 or 301 kind of course. And of course, we'll end with Q&A. So the introduction. The world of the mainframe, as Howard and I like to say, it's mainly a frame of mind. As Jay pointed out, mainframes run mission-critical workloads. And it's honestly not an accident that the mainframe has survived over 50 years in such a fast-paced technology world. It was really architected from the beginning and purpose-built to do so. And hopefully today you're going to get a glimpse into how this has been accomplished and the role that Ficon plays in that space.
Yeah, Patty, one of the really cool things about the mainframe, I think, is, and of course Ficon, is in the little did you know bubble there, what we come to realize is that the very first storage area network was actually introduced on the mainframe when the SCON protocol was added to that to the processor. So what we're seeing here is an evolution of storage area networks from SCON into Fibre Channel and therefore Ficon.
Exactly. So talking a little bit about the purpose of the mainframe, when it comes to businesses that mainframes support, right, it's all about the data. A database holds a company's most valuable asset. Business, however, is accomplished through transactions. And those transactions operate against that data, and they're driven by applications. So storing and accessing that data needs to be fast and reliable in order to support the business of a mainframe. That's where Ficon comes in.
It's kind of interesting that slide actually looks like an image of a data center, but what's really cool, or I shouldn't say really cool, one of the characteristics of that customers expect out of mainframe and therefore Ficon-driven applications is that they're quite reliable, and one of the key characteristics, I think, kind of an interesting thing, is they're mission-critical applications. If those fail, a lot of customers can find themselves on the front page of the Wall Street Journal, which is the last place somebody wants to be. Hence the reason for the kinds of characteristics that the mainframe provides.
Absolutely, and we're going to get into those. The activities of the mainframe, so what you see on this chart is things about mobility and the Internet of Things. These have caused huge increases in the number of transactions that a business must process. If you think about your own self, right, how often do you go online and check out your bank balance or move money around or purchase something online? All of these activities put a lot of pressure on back-end servers, what we call the systems of record, and that's where the mainframe plays its role.
It's interesting that when you talk to a lot of people, especially like your millennials, about networking or the network, they always think of the internet and they think of Googling. The little statistic in the Did You Know bubble basically shows that with regard to transaction processing, there are 20 times as many transactions of value going on compared to the number of Google searches that are happening every second. And that to me is quite impressive. What's even more impressive is that those are occurring without hardly a thought every single day. They're effectively the electrical grid of transactional processing, and without it, we notice it almost immediately. We notice it if that is not happening. Again, that becomes one of those things that is very visible when it isn't done, like losing power in your neighborhood, but taken for granted on a day-to-day basis.
Exactly, right? Those systems of record on the back end are what's taken for granted, what we call the front-end systems of engagement. That's what you interact with all the time. So you know when your phone's not working or your laptop's not working, but it's those mainframes on the back end that you really notice. A lot of people notice when they stop or if they stop, right? Or take for granted that they're running all the time. So these characteristics of the mainframe, this is where our little mnemonic comes in, is faster. And I'm not going to read each of those characteristics for you right now. We're going to go through them one by one and talk about how important they are to the mainframe. The first being integrity. Errors just cannot result in data corruption. Remember, the data is your most valuable asset. So link technologies, when we're looking at storage attachment, link technologies like Fibre Channel, they do provide a level of checking and assurance on the link. But Ficon, as an upper-level protocol, provides higher-level checks aligned with the mainframe standards and requirements.
Those checks are really interesting because what essentially is happening is that Ficon adds a check from the point that the data is sourced to the point where the data is deposited. So it's beyond just the link integrity that's being evaluated, but it's also, if you will, component-to-component integrity that's being ensured by adding the Ficon CRC to all of the transactions.
Second characteristic is security. The resources of a mainframe have to be capable of sharing at an extreme scale, and we'll talk about that a little bit later. But the sharing must also provide real logical isolation and separation. Each of the instances needs to be in their own world, if you will, even though they're sharing physical hardware. Also, when it comes to fiber channel fabrics that connect to mainframes, there are also steps taken to ensure a level of security. For example, in a Ficon environment, we limit the number of switch hops allowed. We require a feature of switches called high-integrity fabrics. And lastly, or another thing, is that I/O configuration is done through a single central authorized means. It can work in conjunction with other fiber channel security constructs such as fabric zoning, But zoning is not required in Ficon environments because of other things in play there.
I think you made a good point there with regard to the hops. I mean, traditionally, Ficon has been a two-hop, if you will, configuration. But what's not completely fully understood is that is really a qualification limitation based upon this security attribute. Essentially, what Z-Systems does is indicate what the topologies that are supported, and then the implementations try to provide features that enforce those topologies. Most recently, multi-hop has been added, but again, it's not any kind of multi-hop fabric that can be deployed, but a very very specific multi-hop fabrics are now supported, and those features came about because of additional functionality that has been put into the infrastructure implementations in order to support multi-hop in a secure fashion.
Next one is flexibility. We all know in the technology world, technology changes quickly, and all systems, including mainframes, have to adapt. We're driven by speeds of feeds. We're driven by things like end of life of componentry. We're driven by the need for new feature and function. But one overarching philosophy of the mainframe is backward compatibility, along with smooth migration forward. The architecture of the mainframe is really the bedrock for enabling this. That architecture does change, it does evolve, but sometimes the underlying technologies are revolutionary, they're disruptive. In a mainframe, the fact that the network and storage are integrated components of the stack, they're not plugins, is a key to also enabling this flexibility.
The transition from ESCON to Ficon is a really good example of how the system architecture abstracted those storage characteristics away from the link architecture. So as we made that transition, we were able to basically take out everything below this red line in the picture here and completely replace it, that transport from ESCON to Ficon, without impacting the existing applications. There was a tremendous amount of development that occurred to make that happen, but that was one of the key characteristics to support a smooth transition for customers from what would be considered the first SANs to the modern SAN.
Next characteristic, availability. The errors must be isolated to limit their impact to a running system. Things will go wrong, but when they do, we must limit their impact. There's also a huge focus in the mainframe on awareness of, and then of course elimination of single points of failure for high availability. Why is that? Look at the chart on the right. Because downtime cannot be tolerated. Downtime, especially during core business hours, is extremely costly.
Patty, is that top line, is that your salary, that $8.2 million a year or per hour?
No, not quite.
That's kind of a boggling number. Can you imagine? I think a lot of the folks who are on the call today would probably be able to relate to those points in time when they've had issues where things have been out and their applications have been down, and these numbers become extremely prevalent. But I can't imagine what it would be like to be in a situation where you were losing $8.2 million every hour you were down. That's just outrageous. Again, those kinds of events land a company on the front page of the Wall Street Journal, which is the last place a company wants to be if you're providing services, which again is one of the drivers as to what the characteristics of the mainframe are. Availability is just without a doubt probably the top characteristics in a mainframe environment.
Absolutely.
Yeah, we call that an RGE, a resume generating event.
Very true. Well, from availability comes serviceability, right? Availability is about avoiding or recovering from errors. Serviceability is about fixing what broke and how you do that. So there are a couple of things that go into serviceability. One is first error data capture. That's our terminology, which is to clearly identify what went wrong. right? To be able to say when something goes wrong, I gather enough information that I can diagnose that failure and I can properly service it. So that's key. But also in a mainframe environment, when you're fixing what broke, that also needs to be done with as little impact to operations as possible. Why? That $ chart on the prior page, right? Whether it's a hardware component that must be replaced or a firmware fix that needs to be installed, to fix a bug, that repair on a mainframe needs to be accomplished concurrent with ongoing operations. You cannot take the system down.
And these characteristics also extend out to the componentry. They extend out to the directors that build up the fabric, as well as to the end devices as well. All directors are created with redundant components so that you can do hot swap of blades or power supplies and things like that. But in addition, the architecture of the entire system is also redundant to make those serviceability characteristics possible. So there's almost always at a minimum of a dual SAN implementation that allows service on one SAN to occur while the production operations are still able to continue on the other SAN.
Next is that focus on transactions, right? And a transaction, it's important to note, goes beyond just a single read or write command, right? It can take many commands and many disparate pieces of data to actually complete an entire transaction. The system architecture of the mainframe and a Ficon enables this to happen efficiently. In a couple of ways that happens is Ficon architecture provides a series of in-band I/O instrumentation and metrics that really give you deep insight into the I/O service times. Every component, how long that operation sat in the channel, how long it was on the link, how long it sat in the control unit, maybe waiting for device access. All of those individual times, with that awareness, it means that we're able to reduce service times more efficiently and use the I/O resources better. Some of these Some of the metrics are used in real time, made for real decision making happening on the on the system, whether it's by the host operating system or some component of the hardware firmware of the system. And other pieces of this data are used in problem debug, or maybe even in looking at data over time. It will spawn an idea for a next technology, a next thing we need to do in the protocol to improve the efficiency of operations. And another thing is flow control. When Fibre Channel, as a base at the Fibre Channel transport layer, they have a level of flow control called buffer-to-buffer credit, and it's great. But at the higher level, right, Ficon as an upper-level protocol provides its own flow control, and it calls that IU pacing. And I'll talk a little bit about that later, very briefly kind of mention it.
And one of the things that comes apparent in this diagram is that there's a lot of sharing going on. That is, all the devices can be shared, the paths to those devices can be shared, and that's all done by the abstraction that's done, the high levels of abstraction that are done in the mainframe. We'll see a little bit more about how that has evolved in the upcoming slides. But in this particular slide, one of the things I think is important to note is that there are path groups that are created that allow a channel or a group of channels to be able to access control units. And that allows them not just one path or two paths, but up to 8 different ways to get at the same data set. And that's very important when we start talking about the volume of transactions that are going to be required, as well as the redundancy at being able to access those.
Talking about that virtualization leads us to efficiency. The original mainframe was just a bare metal box. It was capable of hosting one and only one operating system instance. It has evolved. You might even say it has had some disruptive technology applied. And today, clients can efficiently run hundreds, if not thousands, of different operating system instances on a single mainframe. And they're able to do this because of the virtualization capabilities of the system. The first level of virtualization is referred to as a partition. So I can host one operating system in a partition. But I can also host a hypervisor in one of these partitions. And that hypervisor can host a number, right, possibly hundreds of additional operating system instances. So you can see when I say extreme scale of the virtualization, what I mean here. The physical resources in a mainframe, whether it's the processors or the Ficon channels, they can all be shared across all of the partitions, all of the operating system instances, or maybe just a subset of partitions, or they can also be dedicated to just one of the partitions.
You know, Patty, the virtualization levels that occur here are pretty astounding, as you pointed out. It's almost recursive in nature. You could just go right up that stack, and in those OSs you could add additional layers of virtualization. I think one of the more interesting aspects of it is that because the mainframe is purpose-built to support that, the hardware itself has characteristics in it that allow this level of virtualization to occur. And that's what makes the mainframe unique from other implementations.
Absolutely. It's built into that system architecture that we talk about. The next characteristic, reliability. Obviously, mission-critical workloads demand reliability from their infrastructures. The amount of error checking in a mainframe environment, in mainframe componentry, and across the entire hardware, firmware, software stack is, I believe, truly unequaled. But beyond inside the mainframe, there's also extensive qualification testing that's done on other parts of the mainframe ecosystem, such as switches and storage controllers. And I think Howard can definitely attest to that last point.
Oh, absolutely. You know, this is the reliability piece actually kind of reminds me of a story when we were first building the Model 3 SCON Director. We had one of these test scenarios that I thought was absolutely absurd. It was an 8-hour shift that all that was done was that the system was subjected to the old knife switch on the wall test. So every 10 minutes the knife, power down, power back up, power down, power back up. And we had to get through that 8-hour shift with the hardware and software recovering completely each time. If we didn't make it through the shift, for whatever reason, we had to figure out why, what was causing us not to make it through. And like I said, I thought this was a completely absurd kind of test. But then you do run into, in the real world, similar kinds of scenarios that you want to be able to get through. And I'm reminded of the Northeast brownout that occurred in I think, 2003, where an entire region of the country was suffering from electrical grid failures, and equipment was going through essentially those kinds of problems where power was fluctuating enough to cause, elements of data centers to go out and then come back on and go out and come back on. So it's kind of after that event that I realized that even though the test guys were driving me pretty much crazy with this test, it was with merit, and that in fact they were trying to emulate things that happen in the real world.
Yep. Yeah, the testing is quite extreme.
So let me ask you a question real quick before we get there. So we've been talking about the needs and the requirements of the mainframe environment. For the mission critical applications, we've really got a couple of good examples of what mission critical really means. But is it fair to summarize that part of it by saying that the critical needs of a mainframe are that it always has to work, and it always has to work even over time with new technologies?
Absolutely. Absolutely.
Okay.
There are other examples we could give you of in the transition of link technologies where other things were done to smooth that transition. But a mainframe, we say once you power it up, it needs to be able to stay up, right? It needs, even if we need to service an individual component, the whole thing needs to stay up. Obviously the piece that, if there's a hardware component that you're servicing, that comes out. But everything else needs to stay up, right? The sparing technologies, things like that, so that multi-pathing, so that if I have to take away one path, I still have maybe 7 more that can get out to that device. So I haven't lost anything, right? Operations need to continue. They need to continue with integrity, and they need to continue reliably. And of course,
and so this is the environment that we're pinning Ficon to, right? I mean, these are the things that Ficon has to do in order for it to work. Okay, just wanted to try to set that stage a little bit.
Absolutely, and so we've tried to talk a little bit about, and at the end we'll kind of show you some of the things, but there are many, many things in the Ficon protocol aimed at addressing each one of those characteristics. So let's go into the protocol a little bit here. So Ficon, I'm calling here a tale of two architectures. And the first architecture is the system architecture of the mainframe. That's what's documented in what's called the principles of operations. We lovingly call it the POPs. And it's this system architecture that has really provided that stability for the mainframe and for our clients for the last 50-plus years. That architecture has evolved to provide new capabilities, but always with that sense, as we talked about, of backward compatibility. You can do something the new way, but that's optional. The old way will still work. That application written back in 1964 will still work.
You know, one of the things that we shouldn't lose sight of is that the principles of operations are based upon the customer demands. So effectively, the customers have driven us to providing, as shown in the chart here, the levels of virtualization. So, you know, for example, you've got the mainframe hardware with all of its various purpose-built characteristics, but on top of that, you have the hardware hypervisor and the partitioning in the operating systems. All of that abstracts the applications from ever knowing, you know, what's going on down below. So new technologies can be introduced in a fashion so that the applications can continue to run and do the work that they've been designed to do, yet move the data center, if you will, forward as far as technology is concerned. So it's quite impressive how these principles of operations really have been customer-driven and based upon the demands of their applications.
Yeah, we often refer to the POPs as kind of the mainframe Bible. But as Howard said, there's a part that moves on, and that's the second architecture, which is the link architecture. This is where things have been much more revolutionary and disruptive in nature, where the technology has taken leaps forward. Again, transparent to the application, but a critical part of the mainframe. The physical connections and the protocols that flow over the storage links, as you can see on this chart, have changed drastically over the years. Originally in 1964, we introduced parallel channels. Quite some time later, in 1990, SCON channels were developed. And then in 2000, Ficon is the most recent embodiment of mainframe storage attached channels. The changes are all really driven by the need for speed, the need to maintain competitiveness of I/O rates. And also, when Ficon was developed, it became an ANSI standard, right? The idea was to be open. You know, the mainframe has a real focus on being open now, and so Ficon is an open ANSI standard. It's documented in something called FCSB6. It's the latest iteration of it.
You know, Patty, one of the things that stands out to me here is that, you know, parallel channels were around for quite a long time, and then SCON was revolutionary in its adaptation of fiber optics. But Fibre Channel disrupted that, and so SCON really only had a relatively short life compared to parallel and to Ficon for that matter. And we're looking at 25 years for parallel existence. And with Ficon, we're already at 18 years of Fibre Channel and the marriage between Fibre Channel and Ficon. So there are opportunities out there that can occur where technology that was revolutionary at the time can get disrupted. And the really impressive thing about the mainframe is it was able to absorb that disruption and then provide a transition. And it was not without considerable amount of engineering effort. I'm reminded of the Ficon bridge card and the efforts that went in to make that project work. It's essentially a blade that sits in an SCON director that translates Ficon channel I/O into SCON I/O so that the customers could slowly migrate their storage infrastructure to Ficon while allowing the mainframe to move forward and to deploy Ficon on the channel side. So quite impressive in my mind the way that happened, but also kind of a word of warning for the future as well. You have to be able to adapt, and just as Ficon disrupted SCON, there may be something out there in the future that the mainframe will adapt to as Fibre Channel is replaced or disrupted.
Right, absolutely, and that transition with the bridge card is part of what I was referring to earlier as, backward compatibility, but also smooth migration forward, and that bridge allowed that smooth migration forward for clients. So let's delve into that system architecture first, in particular focusing on the channel piece, because that's what's relevant for Ficon. So channels, and I know I've used that terminology before and I've not defined it until now, but I'll define it now. Channels really represent a path from the host to the peripheral devices. They're somewhat analogous to a PCI bus in the sense that they connect to one or more controllers, and these controllers control one or more devices. In the case of channels, in particular a Ficon channel, there can be multiple different types of devices at the other end of the channel. It could be a disk, it could be a tape, it could be a console or a printer, or it could be what we call channel-to-channel devices, which allows a host to talk directly to a host. The channels, in general, convert from the system architecture, that principles of operations part, to the link architecture. And when you look at Ficon channels in particular, specifically, they convert from that system architecture to the fiber channel transport. As Howard had mentioned, these channels can be grouped into a path group, and where all of the paths in that path group provide access to a particular storage controller or a particular device. And so we'll lead into the next page with that.
And one of the things that occurs to me here is that direct attachment is actually an extension of the bus and tag days. So being able to do direct attach is still supported. But as a switch person, I would highly recommend that any deployment that you have is switch attached, because that's what really allows you to get at the massive amounts of I/O and flexibility in a mainframe network. Not that I have a bias.
Yeah, no bias there, no bias. Okay, so I mentioned the channel paths, and they can be grouped into a path group. That's where the channel subsystem comes in. So this is another piece of system architecture. The channel subsystem is the part of the mainframe that allows the host processor to initiate the I/O operation, tell the system what it wants to do, but then go along on its merry way until the I/O operation is completed. It can do other application processing or whatever. The channel subsystem assumes responsibility for path selection. So if I have a choice of paths that can get me out to that device, then picking one of the paths defined to that target device is the role of the channel subsystem. In open systems, generally where there is multipathing support, that responsibility generally belongs up in the host, inside the operating system. Here on a mainframe with Ficon channels, that is the responsibility of the system itself. The path group was defined, and it will pick and manage those paths.
This is actually one of the for me, one of the more interesting things about Ficon relative to the previous protocols is that previously those protocols were connection-oriented. That is, once the connection was established, that connection remained intact throughout the entire transaction, and that meant those resources were all held until the transaction was complete. With Ficon, it's a connectionless transaction, so it could actually take the system architecture, if you will, the idea of having a lower layer process things. So once the command was issued, the control unit can essentially disconnect from the channel, allowing the channel to initiate yet another command, and it can go to work on gathering up the data and doing what it's been asked to do, and then provide a response later. And that was one of the key characteristics of Ficon when it came about, hence why Fibre Channel was such a disruptive technology to ESCON at the time.
Yes, those switches. Okay, so continuing on, let's look at the I/O operation. So how do we start one of these I/O operations? In mainframe terminology, a target device internally is represented as what's called a subchannel here. So each of the target devices has a subchannel representation inside the host. A subchannel can be accessible by a path group with, as we talked about, up to 8 channel paths. Well, how do I identify a path? Well, that depends on your topology. As Howard was talking about, we support point-to-point connection direct from the channel. The fiber goes directly from the channel to the storage controller. That's what we call point-to-point. In that case, the path is simply identified by the channel path identifier. If, however, you're in a switch topology, it's on the left here, then it's identified by a combination of the channel path out of the host and the egress port out of the switch that connects to the control unit. So if I had another switch in here, if I had cascaded switches, it's still the channel path out of the host into that first switch and the egress port out of the last switch to the control unit. So that's the path definition. The instruction that allows you to start this operation in PrintsOps is called start subchannel. Makes sense, right? If subchannel is the target, it's a start subchannel instruction. So we'll look at that in a little more detail here too.
You know, what's interesting as well is that the system architecture really is detached from the transport. It doesn't really care what's going on there. So the definition that Patty was just talking about kind of emphasizes that. All it really cares about is I know what channel that I'm going to send it to, and I know what control unit I'm going to send it to. What happens in between is really not important, except that it is kind of important because the in-between stuff still has to adhere to those principles of operation that are so fundamental to mainframe environments.
Absolutely, and that's this bridge between system, link, and device, that translation. But the system architecture, meaning maintaining its stability, is what allows a mainframe to continue to evolve. So if we look at this I/O operation, what constitutes this start subchannel instruction? Well, obviously I need to point to the target device. I'm issuing an operation targeted at which device. And then there's a pointer to what's called an operation request block. That operation request block is really just contains, among other things, but most importantly contains a pointer to one or more channel command words. So this is really identifying the work that the operation is intended to do. It gives the command to be executed in a single CCW. There's a command to be executed, the address of where the data is to be stored or fetched from, or potentially a pointer to a scatter-gather list of data addresses, the quantity of the data that I'm processing, and then a byte of flags, which among other things, and there are many things that can be contained in these flags, but one of the key things is that it allows you to chain the CCWs together. So in one I/O operation, I'm passing in a series of commands and data addresses to be processed.
Yeah, this slide is really a demonstration of where our geekness is really showing. But what's interesting about the way that channel command word chains are done is it's not your average scatter-gather list. The commands and flags actually provide information such that these structures, this list of commands, can almost be autonomous, and that's the way how they can be sent from the channel to the control unit, and then that supports the connectionless orientation. So there's a whole bunch of work that's defined there that can be done completely autonomously from the channel. And that's how he can start an operation let go of that device and then start an operation with another device. And that creates a tremendous performance improvements as well as capacity improvements.
So that's not the geekiest chart. We'll come to one later, but we'll move forward anyway. So, and we'll talk about control units and devices. So at the back end of the fabric, so we had the host with Ficon channels. At the back end of the fabric are Ficon storage control units. And just as there is virtualization on the host side that we talked about, these physical control units can also be virtualized in what we call logical control units. So Ficon disk drives are similar in concept to SCSI LUNs, if you're familiar with that, although the device architecture of SCSI versus Ficon controllers and devices is significantly different. And Ficon channels, as we said, can connect to multiple device types. The control units, their role is really to kind of be the mirror of the Ficon channel, where the Ficon channel converts between system and link architectures. The control unit converts between the link and the device architectures. So Ficon disk control units convert between the fiber channel transport constructs and the extended count key data, or what we call ECKD device architecture on the back end of a Ficon disk.
The extended count key data architecture is quite interesting because it allows for variable block sizes. That is that the data can be sized what's most efficient for the application, so that the block sizes on one control or one disk device could be different than block sizes on another disk device based upon the application. Now that's pretty cool.
So let's look at now the link architecture. So we kind of looked at the system architecture. Let's look at the link architecture, which remember is really on both ends, as we said. It's on the system end and it's on the device end. And Ficon provides this protocol conversion between them. It does that translation. What is in the Ficon architecture is a description of what is required, what are the required behaviors on each side of the link in order to execute the I/O operations, what the role of the channel is, what it shall, may, must do in standard terminology, as well as what the control unit, how it should behave in response to operations and events that occur on the link. Within the Ficon architecture, within that link architecture, there are descriptions of the initialization process, how things come up and connect. There are a series of unique link level functions. They're obviously at the fiber channel layer link level functions, but these are at a higher FC4 layer, at the Ficon layer. There are also link level functions that are defined, and how individual operations happen in the good case and how errors are detected and recovered from. These are all the components of what's in the Ficon or FCSB architecture.
The architectural diagram that we have here, actually with the system architecture and device architecture bookending the link architectures, it really emphasizes the fact that the link architecture is doing a translation. But the key piece is something that we've touched on a couple of times here, is that it's not only just translating I/O or block structures or control structures. It's also translating requirements, and that is the things that we talked about in the first half of the presentation, translating the integrity requirements, the security requirements, the transactional requirements, and so forth. And that's what's defined at what Patty's referred to here as the FC4 layer, or the upper layer of the link architecture.
Right. What are the behaviors of these components in order to meet those requirements? So if we look at the I/O request sequence on a Ficon channel, as we said, it starts with the start subchannel request out of the host. Control is transferred over to the channel subsystem, which will do the path selection. And then the Ficon channel does its job. And its job is then to take that CCW chain that was passed to it, the operations that the application requested to be done, and it fetches and processes these commands and data and packages them up into information units defined in the Ficon protocol, which map to fiber channel information categories. And so that's what's documented in the protocol. And then, of course, the adapter will take these IUs and build fiber channel frames from them. When these frames are received on the other end of the link, the Ficon control unit rebuilds those incoming frames basically into the Ficon IUs. It interprets and understands them, and then translates that into the device architecture to tell the device what to do, to store data onto the device or retrieve data from the device.
It should be noted here that the transport in this picture still remains agnostic relative to each one of these functions that are noted here. The reason I like to emphasize that is that being intimately familiar with the link architectures, it demonstrates how the mainframe is able to insulate the applications from the technological changes that occur at this space.
So let's drill down just a little bit. This is where I say the geekiest of all the charts is, Howard, because we're going down a little bit.
Very definitely.
I've seen your charts, Patty. This is not the geekiest.
This is not, well, we eliminated some of the geekier ones, but there's a series of commands. Remember, I can have a chain of commands sent in an operation. Well, because of sequencing controls and checks within the Ficon protocol, multiple commands in this chain can be transferred to the device without waiting for a response for each command, and that's something we call CCW pipelining, and that's where some of that higher level flow control comes in as well. However, in Ficon, only a single CCW command is packaged into one of those Ficon IUs that I mentioned, and a single IU can hold up to 8K of command data. That IU then, remember, is converted into frames. And so as many IUs as are needed to build the information for a single CCW are built, and then as many frames as need to be sent to transfer that IU will then be built by the adapter and sent out on the link. The receiving node is going to rebuild those incoming SC2 frames into an inbound Ficon IU, interpret the contents, interact with the device as it needs to complete the operation, and then, of course, their status, which I'm not really showing, to say how did it all go. One thing I want to note on this chart, and I really tried to simplify it even though it still looks kind of geeky, is the pictures of the FCSB IUs, or a Ficon IU. So they're packaged in an FC frame. So the starter frame, end of frame delimiters, and such, those pink areas are part of a standard fiber channel frame. What's unique to Ficon is what we put in the middle, in the green there. And so it always has an SP header, and then a bunch of other Ficon constructs are stored in there. What's notable here is that, as Howard mentioned earlier, the CRC, when we talked about integrity, the I for is faster, that CRC, that end-to-end checking, is included in every data frame that's transferred.
Yes, I agree. This is the geekiest of the slides.
Yeah, and we can get a lot deeper and geekier in, you know, a Ficon 201 or 301, but I thought this was as deep as we could go here.
And yeah, we certainly hope that there's feedback from the audience to let us know where the Ficon 201 class should go.
Absolutely, absolutely. So this is really the summary chart of the characteristics of Ficon, and I think we, you know, going back to our is faster mnemonic, I think we've really talked about most of these, so I'm not going to read them, but there are three that we probably haven't talked about in the course of today that I'll bring up, and that's focusing first on the flexibility one. So Howard said, you know, Ficon only lives for 10 years. Ficon's been around for, you know, 17, 18 so far, and still seems to have a bright future. But that doesn't mean that it's static, right? That doesn't mean that the Ficon protocol is static. And so, in fact, there are two modes of operation in Ficon. what we call command mode and transport mode. Command mode is the original Ficon. Transport mode was developed later, basically to deliver improved performance. And so a Ficon channel is capable of doing operations in both modes. Another one is availability, this logical paths and multipathing. We talked a lot about multipathing, but what we haven't really talked about is that there's a lot built into the Ficon architecture that maintains the status of the path at all times. So when any state of a link changes up or down, there are link level commands, as I mentioned, that understand the effect of those changes on logical paths. So when the channel subsystem is selecting a path, it always knows what's available and what's not. And then serviceability. There's, I mentioned first error data capture is important, and there's a concept that was introduced in Ficon called purge path, and then later purge path extended, that is really there whenever a protocol error is detected at the channel, it issues this command in order to gather information at various points in the fabric to better diagnose, so we get good first data capture, a view from all of the points along the way of the health of the link and such. So that's really the last slide of today. I hope this overview provided you with a little insight into Ficon and how it fits in the mainframe world. Ficon really does provide mainframe qualities of service while exploiting the best storage attached link technology out there, which is Fibre Channel, and I truly believe that.
Excellent, Patty.
Awesome.
How about an electronic round of applause for Patty Driever?
I'm my sidekick.
Golf clap, golf clap, golf clap. So there are a couple questions that I think that we can probably do some addressing. The timing here is fantastic. We are coming up at the top of the hour, but we have time for a couple of questions. As I read off what we currently have, I encourage anybody listening to provide your own questions. In a broad level, and we can look at this in a deeper way from for a 201 or a 301 course. But when planning for a Ficon deployment versus planning for a traditional x86 fiber channel deployment, what are the key considerations that need to be taken that may be different? Some of the things that may not be intuitive to somebody who's familiar with the fiber channel network.
So,
Jay,
as we said, high availability, configuring the fabric for high availability is probably the most important part of the configuration. And so there are, you want to avoid single points of failure. So there are a series of tools available when you order in order to ensure that cards are plugged in slots that eliminate or minimize single points of failure within the mainframe environment itself, and as well as to help figure out this cabling infrastructure, right? It's quite complex to ensure that you have different paths accessible. You want to make sure you're plugged into multiple switches in the fabric, multiple ports in the control unit, and ensure that you're plugged in single points of failure, taking into account single points of failure constructs within the switch, as well as within the storage controller, and of course within the mainframe. So I think there is a lot of planning that goes in, mostly I would say for high availability purposes.
Yeah, I think Patty hit the nail on the head there, is that planning is the key thing that, or difference that you'll notice between deployment of mainframe systems and open system systems. They're attacking different customer needs, so the mindset for each one is a little bit different. But planning by far is the key aspect, I think, of mainframe environments. So those teams spend an awful lot of time just working through all various aspects and the what-if scenarios, and these are it's demanded by the applications that they're going to be supported to do just a higher degree of planning.
Does that make it difficult to expand or extend the link architecture over time if you've got to do that?
No, I mean, actually, that part of the architecture, the idea of path groups, predates Ficon, right? I think that's kind of a stability thing.
Actually enhances, those characteristics enhance the ability to do changes, really. Initially, best laid plans, of course, right, of mice and men always go awry. But the fact that you spent a lot of time establishing the plan for the system architecture and then can adapt to it, that's also built into the overall architecture.
Another thing of the mainframe, right, if you need to add more Ficon channels, let's say, to your configuration, and there are slots available in the host to add more channels, that can all be done non-disruptively. You can not only add the physical cards into the system, but you can dynamically have them added and recognized by the operating system. So you don't have to take anything down. So, I mentioned you don't take it down for service, but you also don't take it down for configuration changes. There's the ability to add and delete resource non-disruptively.
Well, that actually dovetails in with a couple of the questions that have just come in that involve that very question about moving forward into new technologies. So one of the questions is, do you see the Ficon link speed sweet spot adoption moving from 4 to 16 gig with the introduction of forward error correction?
And yes, I mean, we're already at 16 gig with forward error correction, and then of course 32 gig is the next step, and 64 somewhere down the road. But today's mainframes already support 16 gig, and I think that is probably going to be a sweet spot for a lot of clients for a while.
Yeah, absolutely. And I think the insight on forward error correction is really key there. Remember, at 16 gig, forward error correction is optional, and the Z-System environment actually was the first to provide an end-to-end forward error corrected speed bump at 16 gig. As that becoming the sweet spot because it's going to provide a better integrity, I definitely see that as a major factor.
Cool. Well, as we get to the end of the hour, there's one question in particular that I do want to address before we close out. Are there planned improvements in Ficon to address the fact that the underlying storage is under migration to randomly accessible media and SSDs? In other words, NVMe for Ficon?
Okay, so this is where kind of this layered approach maybe really helps out, right? Remember that on the control unit side, it's converting to device from the link architecture, so from Fibre Channel to the back-end device architecture. So I think the first place, particularly in the mainframe environment, that you're going to see NVMe is maybe replacing some of the existing SSD or spinning disk, the back-end devices in a storage controller. So it would still be, it's really transparent to the transport as well as the host. The possibility for actually utilizing the FC NVMe protocol, I think, is a little further down, but I think that's a realistic possibility for the future too.
And I would say that this is mostly going to be driven by the demand from customer applications. So depending upon where customers are moving or migrating their data, then the demand for where NVMe shows up in the mainframe space will become clearer.
Makes sense. We're really pushing up at the top of the hour, and we're going to have to push out the rest of the questions into a Q&A block. And obviously, there's a lot of depth to Ficon that we weren't able to cover due to time, and especially for those of you who really like the geek stuff. We probably excised 3 to 4 times the amount of information that explore how Ficon works. And we do hope to be able to turn that into a deep information base for a 201, 301, or even 401 sessions in the future. In the meantime, you can join us next time as we dive into some of the more interesting aspects of Fibre Channel, that of interoperability. We've been getting quite a few questions about this, and so we've decided to bite the bullet and address this sensitive issue. Now, after this webcast, one of the things that we really need is your feedback. So please click on that feedback and vote buttons. It helps us understand what kind of information resonates the best with you, It also helps us improve the webinars in the future and see what works and what doesn't work. Also, it really means a great deal to the speakers who really do this out of the goodness of their hearts and their love of the technology. And for this reason in particular, it's valuable, extremely valuable, to let them know how well that message is being received. Now, as I mentioned at the beginning of this webinar, we're going to post a Q&A blog on fibrechannel.org for these questions that we've covered, as well as some of those that we've not able to get to. And there you'll be able to find a PDF of the slides as well. Give it a little bit of time as we can, so we can upload it. One of the ways you can find out about where these are posted and when they're posted is to follow us on Twitter at FCIA News. And of course, we have a lot of additional content that you can learn about Fibre Channel, straight from the horse's mouth, so to speak. We're trying to cover everything from the basics, like what we just learned today about Ficon, to new technologies such as NVMe and the future roadmap, to some of the less sexy and yet very important aspects of deployment, such as cabling. So, as a final note, we have a couple of additional references for you to find out more information. We'll be putting these into the original blog entry, at least until we can provide a Ficon 201 or higher level courses. So please check out the fibrechannel.org website, and you can find out all of the latest and greatest information. So speaking on behalf of Patty and Howard, as well as the whole of FCIA, I really want to thank you for joining us today. We've been working hard, very hard, to provide top-notch education about all things Fibre Channel, and with your support, we will continue to do so. So please feel free to share this information to people for whom you may think this is valuable. And don't worry, we'll make lots more. Again, please submit some feedback in the votes because they are extremely valuable for us to develop more valuable content. So thank you, Howard. Thank you, Patty. Really appreciate this, and I'm looking forward to the next edition.
Yes, thank you, Jay, and thanks to the audience. Appreciate your time today.
Definitely. Thank you all.
Take care. Have a great day.
Bye-bye, everyone.